This problem's giving us the equations, the sine of 2x times y equals x. And then it's asking us to find dy dx, which is them asking us to find the derivative. So let's look at what we have. So we've got the sine of, remember that's of and not multiplied, sine of 2xy equals x. When you look down at a problem like this and you're being asked to find the derivative, whenever you see x's and y's starting to sort of commingle together within a problem, really that's your identifier screaming out that what you're looking at right now is implicit differentiation. So implicit differentiation was a little bit more of a process than our standard differentiation process. And my rule for implicit differentiation is every time I take a derivative, I get extra stuff. And what that stuff is going to look like is we're going to have this, we're going to ddx it or ddt it depending upon the problem. You're going to get d and then whatever the letter is you took the derivative of over x. So every time we take a derivative, we're going to get our extra stuff. The process looks like this. You start off by wrapping this equation in a set of parentheses and you're going to ddx it. You know what to do on the bottom. You know what to dd whatever here based upon whatever's on the bottom of what they're asking you for. If this was dy dt, then I'd be ddt'ing everything, if you can say that 5 times fast. So what we're going to go through and do is we're going to take the derivative of each of these chunks. So I start off and I take the derivative of the sine of 2xy. Looking at that right now, you know, the first thing you sort of notice is that it's got a sign in it. And so your brain's telling you that this is going to be a special case derivative. And it is, because all of our rules from normal derivatives work the same with implicit differentiation. So the product rule, the chain rule, the quotient rule, the power rule, and all of those special case derivatives, that's what we're still doing on all of these problems here. So this time we're talking about the sine of x. The derivative of the sine of x is the cosine of x. The one thing to be careful of on any of these special cases is as soon as that, whatever was inside your special case here, as soon as that is more than just an x, negative x, 3x, anything more than just your basic x, it's a chain rule problem. And so because we have to still watch out for all of these rules, and we look over and say, oh, I definitely have something more than an x going on inside my sine function right now, that tells us that we need to go ahead and start applying the chain rule. And so the chain rule saying that I use goes d in times d out. So the derivative of whatever got plugged into your basic function times the derivative of the outside. So looking at our problem, again, the 2x times y, that was what got plugged into our sine function. So our inside piece is 2x times y. Looking at that and saying, okay, so how am I going to take the derivative of that? What's my derivative of the in? Well, there, again, you always have to watch out for all the different rules that still existed. And so what you've got there is two things being multiplied. And when you have two things being multiplied, that's when you need to use the product rule. So whenever I've got something times something, that's always a product rule. My saying for the product rule is fg prime plus gf prime. I label one chunk the f piece, the other chunk the g, and then I run and go find my g prime and my f prime. So looking at this problem right now, my f would be 2x, my g would be y. So breaking that down, f is 2x, g is y. And I need to find the derivative of those. So I take the derivative of 2x. I took the derivative of 2x, that gets me 2. I am doing implicit differentiation. So every time I take that derivative, I get extra stuff. Because I took the derivative of an x, I'm going to fill that little box in on top there with an x. So I get dx over dx. Then I go to find the derivative of g. Again, take the derivative like you normally would. The derivative of y, that's a power rule, that would be 1. I took the derivative of a y, so I get a dy dx. I filled that box in with a y this time. So then putting all of that together to get me my d in, which is really where I was going for all of this, taking the derivative of my inside piece, I'm now following my product rule. So the product rule says first go grab f. So I go grab f. Multiply that by g prime, so the derivative of g, I don't really need that 1, and so this would just be dy dx, plus from the rule says go grab g, so my g is now y, and then my f prime comes after that. That would be f prime. So one thing you can do is whenever you have a dx over a dx, that cancels out. That's like having 5 divided by 5, right? Those 5s cancel out and you're left with a 1. So anytime we get a dx over dx, that'll cancel out. So my f prime is really just going to be 2. So that's my dn as I start putting together my derivative here. So the derivative of the inside is now going to be 2x dy dx plus, and then rearrange that y over 2 to become 2y. So that's my d in right now from my chain rule that I'm following. The derivative of the outside on this is this sine function. So the derivative of the outside is going to follow our special case. The derivative of sine is cosine, and then you leave alone all the stuff you already took the derivative of. So you leave alone whatever was inside there. So that is our d in, d out move. And when you're doing the chain rule, only the d in gets the extra stuff. This is a rule that has multiplication going on, so that one extra stuff from the d in counts for both pieces. Now we go on, keep finding our derivative. Nothing left on that side, but on this side I'm taking the derivative of x. The derivative of x is 1. Took the derivative of an x, so I get dx dx. So now that you've got all your derivatives taken, you've got to get back to what you were really trying to do, which is find dy dx. So for us, what that means is we're going to need to take the dy dx and treat it like any other variable in the problem and solve this algebraically to get dy dx by itself. So the first thing we're going to do in this is we're going to go ahead and distribute this cosine back through this whole chunk here. So this is now going to be 2x cosine of 2xy dy dx. Multiplying it to the second piece, multiplying it by this 2y here, we get 2y cosine of 2xy. And that's all going to equal, again, dx over dx cancels out, so that all equals 1. From there, we now go ahead and get all the stuff that doesn't have a dy dx on one side of the equals, and everybody that has a dy dx stays on the other. So we're going to move this one piece here, this 2y cosine 2xy, over to the other side because it does not have a dy dx in it. And so that's going to leave us now with 2x cosine of 2x times y dy dx, and all of that is going to equal, on the right hand side we get 1 minus 2y cosine of 2x times y. Last little move here for us is now that these two things are being multiplied, and that's all that's with our dy dx, we can now divide this off of there. So we divide by 2x cosine of 2y, and then do the same thing on this side. And so now these pieces cancel and we're left with dy dx equals 1 minus 2y cosine of 2x times y over 2x cosine of 2xy. So that's our final derivative, and now you just kind of go back and look and see if you can find it in your answers, and sure enough our answer would match answer D right there. Thanks for watching my video. If you liked it, please click that like button and subscribe, and also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.